My name is Sankaran Mahadevan. I am the John R. Murray Senior Professor of Engineering here at Vanderbilt. The fourth subgroup involves topics which actually feeds into all the three subgroups, because this deals with model uncertainty. Now, all the three topics that I talked about earlier, whether it was reliability analysis or structural health monitoring or optimization, they're obviously being done with computer models. So the natural question is, how good are your models? So that's the topic of this fourth group, model uncertainty, or in general, uncertainty quantification. So when we talk about uncertainty, there are several issues. One is, of course, if you take a system that you're trying to analyze, there are the inputs to the system. So you are trying to figure out what are the uncertainties regarding the inputs, and then you are somehow trying to propagate them through, let's say, some computer model like a finite element analysis or something. And so there are also approximations and assumptions built into your model, and then how you solve those equations, all the numerical approximations that you make, introduce further errors and uncertainty in your model predictions. So we typically address these uncertainties through various activities. We do what's called model verification and model validation. Verification has to do with how well you are solving a given set of equations, meaning how approximate is your solution. So we look at discretization errors and convergence studies to figure out how good your solution is compared to some benchmark solution or exact solution, if you know it. Then there is model validation, where you are asking the question, how good is your mathematical model to begin with? Meaning you have some physics which you are idealizing through some mathematical equation. So how well does the mathematical equation represent the reality? So this is validation, and this is done by actually comparing your model prediction against physical observations of the system or by well-targeted experiments. So we have done a lot of work on model validation and also verification, especially funded by Department of Energy and in collaboration with Sandia National Labs for the last 12 years. And we have also been funded by other agencies, including other departments in Department of Energy and US Air Force and NASA and so on. So there is a third aspect, which is calibration. You also have to calibrate the parameters of the model by comparing your model against some experimental observations. So we, of course, have heavily used Bayesian techniques for all of these activities, especially for model validation and for model calibration. And what we have found is that these Bayesian techniques also help us to combine information that is coming from many different sources. So as I was talking about the structural health monitoring, here also we are looking at combining information from many different levels, whether it's material or component or subsystem or system, or from many different sources, whether it's mathematical models or experimental data or literature or expert opinion and so on. And so we use a Bayesian network concept to combine all this information, integrate this, so that we can roll up all of this uncertainty information to a system level prediction, so we can quantify our uncertainty in the system level prediction. And this is a problem of serious interest, because more and more the modern large systems are becoming difficult, expensive, and sometimes impossible to do full-scale testing. You might be able to get away with maybe one test at the most. So all of your analysis and prediction is based on models at the system level, but of course you will have data and system tests, subsystem tests or component tests. So the question is, how do I integrate all this information in a meaningful way? So we are pursuing the Bayesian network concept heavily for this type of integration. And another thing that comes up in this regard is, of course, these computations are expensive. It takes a lot of runs, and if you're going to do uncertainty quantification on top of that, typically you have to use some kind of Monte Carlo simulation or some iterative procedure, which also means you're going to be running these codes over and over again. And so if you were to actually run full fidelity physics codes, that will be almost impossible to do. So we also are doing a lot of work on surrogate models, basically developing inexpensive surrogates for the actual full fidelity code, or a reduced order model. So we have several folks in our group working on this. For example, my student Ghina Nakad, she's funded by the project from Air Force Office of Scientific Research, looking at this combination of surrogate modeling and model fidelity choice. Somewhere you might have a reduced order model, somewhere you might have a surrogate model, and occasionally you will need a full fidelity model run also to calibrate these models and so on. So what is the best combination of resources for all these different types of models that are available? So Ghina is looking at this. And we have this Bayesian network integration work that I had mentioned, this MEMS device before. So Yuling is looking at multi-scale, multi-physics modeling, where information is coming from many different levels with different mechanisms, how all this information has to be combined together in order to assess the reliability or life prediction of this MEMS device. So uncertainty quantification is something that is very important for complex systems design, operation, maintenance, and risk management. And so the risk does not come only from just natural variability, but it also comes from data uncertainty and model uncertainty. So a lot of our work, even in the groups that are doing health monitoring or design optimization or reliability analysis, they draw very heavily on this uncertainty quantification work, in particular model uncertainties, whether they are coming from approximate solutions of the equations or whether they are coming from our assumptions about the physics of the problem. And so currently we have quite a wide spectrum of projects, as you can see, and dealing with the systems that are civil infrastructure, mechanical, even electromechanical and aerospace systems, and dealing with a variety of materials, and also many different types of modeling platforms and computational techniques, as well as experimental activities to validate some of our predictions.